Okay, so chapter 12 will be a short chapter. The goal of this theorem will be to prove the fundamental theorem of Galois theory. This first video, we're just going to remind ourselves some notation. So suppose that we have a field extension. Usually this will be within the complex numbers. It doesn't need to be though. With the Galois group, we're going to just use the Galois group of the extension. We're going to use the symbol G to represent that. Again, this is the set of all automorphisms that fix the subfield K pointwise. Okay. All right. So we have a field extension. From that, we can extract its Galois group. There's two sets here. There's the set of intermediate fields, which I'm going to call script EF. Script EF is one of the ways we can write it is M is a subfield. Let me write it like this. K contained in M contained in L, M subfield of L. So it's the subfields of L that also contain K inside of them. Right? So these are if you like, this is the set of intermediate extensions. It's all ways of filling in the gap between K and L. And just as a quick reminder, K and L, I know K and L are sets, but this is again a set of fields. So K and L are here because you can fit K and L inside of in between, of course, K and L because it's subset or equal to. And then we have G, script G, which is going to be the collection of all subgroups of G. So H is a subgroup of G. And it looks like maybe we should have a mirror situation where where H should have to contain something to make it match F. If you like, we could think about this as just the set of all subgroups, of course, are the set of all subgroups that contain the trivial subgroup. So we could add on that H contains a trivial subgroup, in which case we'd have like a mirror situation, but it's redundant to write that. All right, so we have these mappings. The Galois correspondence itself was mappings. And I'm going to use the notation of your book. So the Galois correspondence is a pair of mappings. Asterisk, or I'll write star, from F to G, and dagger from G to F. And these are superscripted because really we have to fill in an argument here. Okay. So star goes from intermediate fields to subgroups of the Galois group, and dagger goes from subgroups of the Galois group to intermediate extensions. And these were defined by, all right, so to plug something into star, it has to be a subfield. So M star is the Galois group of L over M. Okay. Any automorphism of L that fixes all of M, so I fix all of M, must necessarily fix all of K, because K is contained in M. So this makes sense to say that this is a subgroup of the Galois group of L over K. That makes sense to say. And if I have a subgroup of the Galois group, this is the H dagger is the fixed field of that subgroup. So it's a collection of all L's in L such that H of L equals L for all H in H. So it's the, if you like, it's the intersection of all the fixed loci of each element of H. So we could even write it like this: intersection on H and H, the things in L that are fixed by H, where L upper H is that is the fixed locus via the action of the element H. All right, so certainly every element of the Galois group fixes K, right? G is the automorphisms that fix K. So everything in H, being in the Galois, H is a subgroup of the Galois group, so everything there fixes all of K. So certainly also H dagger, this is not really, it's just a comment. Also, H dagger is in fact an element of F. It's an intermediate extension because K is certainly fixed by all of H. So these are well-defined maps. And this was our Galois correspondence. And in this chapter, we are going to establish conditions for when star and dagger are mutually inverse bijections of sets. And so all that means is we have these two objects, these field theoretic objects on the F side, and these group theoretic objects on the G side. We shouldn't, in general, expect them to be necessarily bijective, namely all subfields of the all intermediate extensions correspond to subgroups, but there might be conditions on when this is a bijection, where subgroups are in one-to-one correspondence with intermediate extensions. And that's part of the fundamental theorem of Galois theory. Okay? So we're going to do that in this chapter.